Hi guys, today we'll show you how to solve this number theory problem from Waterloo's grade 10 Cayley contest. This is question number 22 from year 2018, and it reads that if n is a positive integer, let n factorial represent the product of integers from 1 to n. For example, 4 factorial is 4 times 3 times 2 times 1. If x and y are integers, and let 30 factorial over 36 to the power of x times 25 to the power of y, right? Let this expression equal to an integer. What is the maximum possible value of x plus y? So first, let's recognize that it is a divisibility problem because you want the result of one number over another to be an integer. But also pay attention to the restrictions on x and y, right? X and y are integers, but not necessarily positive, right? So that means x and y can be negative. If x and y were to be negative, then we know the effect of a negative exponent is that it flips the expression. So for example, if I have 1 over, say, 2 to the power of negative 2, right? The negative flips the fraction such that this becomes 1 times 2 to the power of positive 2. So if x and y are negative, then we won't have this divisibility problem anymore. However, in this case, we will not consider the case where x and y are negative because we want to maximize the sum of x plus y, right? So you want each individual component to be as positive as possible. So therefore, given the context of this optimization problem, you want x and y both to be non-negative. All right, if we're solid on the concept of divisibility, then we will know how to approach this problem. So let's first review the key ideas of divisibility. If an integer n is divisible by another integer d, right, positive or negative doesn't matter, then n must also be divisible by all the factors of d, including all the prime factors, right? So that's the kind of the formal definition, but my personal understanding is this. Let's first prime factorize n and d, right? So we'll have some factors of 2, 3s, 5, 7s, all the prime numbers on the bottom and the top. Then n's prime factorization must contain d's prime factorization. So which means all the factors, prime factors in d's prime factorization must be present or at least contained inside n's prime factorization. And the reason I focus on prime factorization is that a number, integer, can have many factorizations. For example, 12 can have 1, 12, 2, 6, 3, 4. However, each number has only one prime factorization. Let's illustrate this idea of divisibility using some examples. Suppose I want to divide 14 by 12, right? I know that 14 is not divisible by 12, but why is that? Well, let's prime factorize 14 and 12. So 14 becomes 2 to the power of 1 times 7 to the power of 1. So that means it has one factor of 2 and one factor of 7. Whereas 12 has two factors of 2 and one factor of 3. We see that the two factors of 2 on the bottom inside the 12 is actually not contained on the top, right? So that means 14 doesn't have enough 2's to divide out the two 2's on the bottom. In addition, 14 cannot accommodate or divide out the 3 on the bottom. Therefore, we know that because if there isn't enough accommodation for 2 and 3, 14 is not divisible by 12. Take a look at another example, 180 divided by 12. We know that 180 has two factors of 2, two factors of 3, and one factor of 5, right? So two factors of 2 on the top can divide out the two factors of 2 on the bottom. The two factors of 3 on the top can also divide out the 1, is more than enough to accommodate the one factor of 3 on the bottom. And the one factor of 5 on the top is just there for cosmetic purposes. So therefore 180 is divisible by 12. Now let's shift our attention back to this question. Is 30 factorial divisible by 36 to the power of x and 25 to the power of y? Well, following the concept of divisibility that we just discussed, let's first prime factorize both the top and bottom. So on the top, you have that 30 becomes 2, 3, 5. 29 stays because itself is a prime. 28 becomes 2 to the power of 2 times 7 to the power of 1, and so on. On the bottom, we have that 36 becomes 2 to the power of 2 times 3 to the power of 2. And 25 becomes 5 squared. Now, in order to compare the top and bottom, we need to group all the like factors together. So we do this using exponent laws. On the bottom, right, we have that multiplicative property that gets you 2 to the power of 2x times 3 to the power of 2x for the 36 to the power of x. Then for the 5 squared to raise to the y just becomes 5 to the power of 2 times y, right? On the top, imagine you have prime factorized all the 30 numbers, then you should be able to group all the 2's together, all the 3's together, and all the 5 together, right? So pay attention, we only care about the factors of 2, 3, and 5, right? Because 2, 3, and 5 are all the prime factors you have on the bottom. We don't care about the 7, 11s, and 13s, right? So if you group them together, let's suppose there are A factors of 2 on the top, right? There are B factors of 3 on the top, and C factors of 5. Remember, in order for divisibility to be accomplished, we require that the exponent on the top to be greater than or equal to the exponent on the bottom, right? So for example, look at the exponents of 5, we should require that 2y should be less than or equal to C. And similarly for 2x, we should be less than or equal to B. And for the 2 factor, 2x should be less than or equal to A. So the next question we have to deal with is, what is the value of A, right, and B and C respectively? I created this table, right, of the prime factorizations of all the numbers before 30, and I look at the number of 5, 3's, and 2's that each contribute. And we see that together there are 7 5's, 14 3's, and 26 2's, right? So therefore we plug in the values for the 3 inequalities. And now let's solve the inequalities to get us the inequalities for just x and y, right? So if 2y is less than or equal to 7, we know that y must be less than or equal to 3.5, right? And given that y is an integer, so y has to be bounded by 3. For x, we have 2 inequalities. We have 2x is less than or equal to 14, and 2x is less than or equal to 26. We take the more strict one, right? So if x is less than or equal to 7 and less than or equal to 13 at the same time, we just require x to be the more strict inequality, which is less than or equal to 7. So therefore, we know that x is bounded by 7, y is bounded by 3, so that x plus y is bounded by 7 plus 3, which is 10.